Okay, day 6 of our unit on derivatives. Today we're going to be talking about differentiable functions and what that means. So the first thing I want you to do is I want you to graph the derivative of this piecewise function. Notice we do have the equation up here, so I know that this branch over here has a slope of 1 because the derivative d dx of x plus 2 is 1. The slope of that linear branch right there is 1. So if I sketch my derivative in red, I know the slope at that point is 1. So I need to draw an open circle there over to the smallest x value I have, which is right there. And that is a horizontal line because the derivative is a constant value of 1 there. Slope of a linear equation. Next bit I see is x squared minus 1, d dx of x squared minus 1. The derivative of x squared minus 1 is 2x. So I know that that function is 2x. So think about what 2x looks like. Well, it's got an x-intercept right there. The slope is negative 2. So it's going to come down to this point. And then over here, it's going to go up 2 over 1. So it's going to hit that point. It's going to go up 2 over 1 again. So then it's going to end up like up here somewhere. And let's connect all of that as such. And that is my derivative function. Now, huge idea here. Notice open circle, open circle, open circle, open circle. Because we don't have any graph defined over here, the right-sided limit of the derivative does not exist, so we're marking that as a open circle. Remember, after all, finding a derivative is a limit process, and you cannot find a one-sided limit if the function doesn't exist on that side. So the points there have to be open circles. So 2 goals here. First one, understand what it means for a function to be differentiable. And then we want to solve some piecewise puzzles. So I want to take you off on a tangent here. In my geometry class this year, we talked about conditional statements. We've been doing a lot of proofs, if P then Q. So, for example, if a samurai chops off my arm, then I will bleed, or I should say my arm will bleed. The contrapositive of a conditional statement, if P then Q, says if the conclusion is false, then the hypothesis is false. So if not Q, then not P. And not false, I meant to say the opposite. If the opposite of the conclusion is true, then the opposite of the hypothesis is true. Conclusion being Q, hypothesis being P. So if I'm not bleeding, then a samurai didn't chop off my arm. Because if a samurai chopped off my arm, I would be a bloody mess. What's cool is that in logic, the contrapositive is absolutely equivalent to the original condition and conditional statement. So think about this theorem right here that we have, theorem 4.1, that says the differentiability of a function implies the continuity of a function. Now, we don't even know what the differentiability of a function means yet, but we do know that if a function f is differentiable at x equals c, then f is continuous at x equals c. So write that as the contrapositive. Take it in the opposite direction. If f is not continuous at x equals c, comma, then f is not differentiable. Again, you take the opposite of the conclusion. If the opposite of the conclusion is true, then the opposite of the hypothesis is true. If f is differentiable at x equals c, then f is continuous at x equals c. If f is not continuous at x equals c, then f is not differentiable at x equals c. Big idea here. If we want a function to be differentiable at a given point, then it absolutely has to be continuous at that point. If it isn't, then it's automatically not differentiable. But okay, what does it mean to be differentiable? For a function to be differentiable, we need two things. We need the function to be continuous, that's what we just said, but we also need the derivative to be continuous at whatever specific value we're looking at, but generally speaking, we're going to be looking at the functions as a whole. If it is differentiable at every single point, then it is everywhere differentiable. So if you think back to the warm-up problem, sketching this graph here, we can see that this function is super-duper not differentiable, both because the original function is discontinuous and because the derivative is also discontinuous. So if we have a function here, f of x, a piecewise defined function, x plus 1 to the left of the x value of 1, 3x minus 1 to the right of the value of 1, we want to know, is this function differentiable? Well, for it to be differentiable, we need the function to be continuous at this point. So we need the left-sided limit, which is x plus 1 as x approaches 1 is 1 plus 1. We need the left-sided limit to equal the value of the function at 1, which is the same as the left-sided limit in this case, to equal the right-sided limit. So 3 times 1 minus 1. So is 1 plus 1 2 equal to 3 times 1 minus 1 2? Yes, it is. This function is continuous at x equals 1. That's what we did last unit. But now we also need to show that it is differentiable by showing that the derivatives are either equivalent or not equivalent if it's not differentiable. So if you think about that function, the derivative of x plus 1 is 1, and the derivative of 3x minus 1 is 3. 1 is not equal to 3, so the derivatives are not equivalent at the x value of 1, so this function is not differentiable. Let's look at another one here. X squared plus 1. So first off, we need two things here again. We need f of x to be continuous, and we need f prime of x to be, wow, I can't write things, to be continuous. I can't even abbreviate things. So check the function first, because if the function is not continuous, then there's no way this function is differentiable. So plug in your x value, set the branches equal to each other. 2 squared plus 1 is equal to 4 times 2 minus 3. Is that true? 2 squared is 4 plus 1 is 5. Is that equal to 4 times 2, which is 8 minus 3, is also 5. So yes, f of x is continuous. If we want this to be differentiable, we need the derivatives to equal each other at that point as well. So x squared plus 1, derivative of that is 2x. Is that equal to the derivative of 4x, which is 4, at the x value of 2? Plug in 2. Does 2 times 2 equals 4? Yes, 4 equals 4. So f prime of x is also continuous. Since the function is continuous and the derivative is continuous, we say that, yes, this function is differentiable. Yes, it is differentiable. So let's compare the two graphs of these last two problems. Here we had one branch, so x value of 1. We had the function x plus 1 when x was less than or equal to negative 1. So x plus 1, we are going to be looking at that function right there. Compare that to the other side, 3x minus 1. 3x minus 1 has a much steeper slope here. So think about what that function is going to look like. 1, 2, 3. That slope is much steeper. So if I draw that side in blue, again, notice we found that they were continuous there, so I know the x value is going to be the same, but I'm much steeper like that. So think about right here, the slope is 1, and right here the slope is 3. And I can recognize in that graph by that kind of abrupt little angle that I get there. If I were to over-exaggerate it a little bit, then I have something like that going on, a sharp edge. A function cannot have a sharp edge like that. If it does, it means there is an instantaneous change in slope, and your function is not differentiable. So compare that to this thing, where we have x squared plus 1 to the left of the x value of 2. So x squared plus 1, we found they're going to have the y value of 5. 1, 2, 3, 4, 5. So we know that that point is right there. X squared plus 1 is going to look like that to the left of there. And then we have 4x minus 3 is going to look like this. If I draw it in red, it's going to be much steeper. It's going to start here, but at that point right there, it's going to have the same exact slope, and then it's going to stay linear forever. But we don't get that situation where we get the little like angle thingy going on. We get like a nice smooth curve through there. So this function is differentiable. So let's see if this one is, again, check and see if it is continuous. 2 squared is 4. Negative 4 plus 5 is, negative 4 plus 5 is 1. Plug in the other value. 2 minus 2 is 0. 1 is not equal to 0, so automatically this is not differentiable. So don't do a bunch of work if you don't have to. Just plug in your function. Plug in your value, make sure it is continuous. So now we're going to look at some problems that you probably could have guessed were coming, the unknown value problems. So we want to make this function differentiable everywhere. So we need the two branches to equal each other at the x value of 2, and we need the derivative of the two branches to equal each other at x equals 2. So start off with that first bit. We need ax cubed to equal x squared plus b when x equals 2. So I'm going to write that as 8a equals 2 squared is 4 plus b. I'm going to leave that alone for now until I know how I want to simplify it. Now that came from the functions being continuous, and now I need the derivatives to be continuous as well. So the derivative of ax cubed is 3ax squared, and we want that to equal 2x, and that is all, because the derivative of b, your constant term, is 0. So again, the x value is still 2, so 2 squared is 4 times 3 is 12a equals 2 times 2 is 4. So I can divide both sides by 12 and get a equals 4 over 12, or another way to write that is 1/3. And now I can plug into that equation to get 8 over 3 equals 4 plus b. I can get 8 over 3 minus 12 over 3 equals b. Notice what I did there. Haha, fractions. 8 minus 12 is negative 4/3 for my value of b. So what we're saying is that nope, not that. What we're saying is that we have the piecewise function. A is 1/3 x cubed for x less than or equal to 2. And then we have x squared plus our b value, which is negative 4/3, so x squared minus 4/3. We're saying that if you graph these two functions, it will transition smoothly from the top branch to the bottom branch. There will be no abrupt changes, no instantaneous changes in slope. So that's the basic gist of the problem, and then you can cruise on from there, write an equation to set the functions equal to each other, and then write an equation to set the derivatives equal to each other. So do this problem real quick, see what you get. I'll do this one more for you. Kx squared equals kx cubed minus 21x plus c. Plug in the x value of 3. So 9k equals 27k minus, 21 times 3 is 63 plus c. And write your other equations using the derivative. So the derivative of kx squared is 2kx, equaling the derivative of the bottom branch is going to be 3kx squared minus 21, and the constant term goes away. So again, start solving what you can solve, simplifying what you can simplify, combine like terms where you are able. So since our first equation doesn't have any exponents, I'm going to solve that equation and see where it goes. And I'm totally lying because it's super late. What I'm going to do is I'm going to finish writing my second equation with plugging in the x value of 3. So I'm going to get 2, I'm not going to get that. I'm going to get the x value is 3. So I'm going to get 3 times 2 is 6k equals 3 squared is 9 times 3 is 27. K minus 21. And now I'm going to figure out what K is. So I'm going to subtract 6K from both sides to get 21K. I'm going to add 21 to both sides to get 21. And so I will see that K equals 1. And now I can plug into my other equation to find C. So I get 9 equals 27 minus 63 plus C, which becomes C equals some number. I believe C is 45. So I'm not going to do this problem for you. It's the same exact idea. Set the functions equal to each other and set the derivatives equal to each other. And solve the system of equations. So do this and then check your answer. Pause, pause, pause. You should find that K equals negative 3 and C equals negative 75. So now same idea, except we have 3 branches. So we're going to do the same thing, but at both x values. So first set of equations, you're going to get kx squared plus c equals jkx. And we're going to do that at the x value of 2. So we're going to get 4k plus c equals 2 jk, and I'm going to leave that for now. Then I'm going to take my derivatives and set them equal to each other. So I'm going to take the derivative of kx squared plus c, and I'm going to get 2kx equals the derivative of the other side. Jkx is a linear function, so I'm going to get jk, just the coefficient there. But again, the x value is 2, so I'm going to get 4k equals j. Okay, and I can't do anything with this right now, so I'm going to leave those as they are, and I'm going to move to the other x value now. So now look at the x value of 4. Set those two functions equal to each other. So in doing so, we're going to get j, k, change back to my blue so I don't confuse you, j, k, x, that function is equal to jx plus 4x, but remember the x value is 4, so I get 4jx equals 4, 4jk is what that should say. So jk, that should say 4jk. 4jk equals 4j plus 16. And let's see what we can do. Can we do anything? No, not really. So I'm again going to leave that for now. And I'm going to go to take the derivative of each to get jk is equal to the derivative of jx is j plus 4. So you might be like, well, what do I do now? But what I want you to recognize is that look back at this equation over here. We have 4k equals jk. So how about we divide by k on each side to get 4 equals j. And now that we know one of our values, we can start plugging in. Notice this equation has j and k, so if we substitute in our j value, we can get 4k equals 4 plus 4. So we can get k equals 2. And now we have our k value as well. So we've got j, we've got k, we just need to find c. So plug j and k back into the other function over here. 4 times k is 2, plus c equals 2 times j is 4 times k is 2. So on the right side there, 2 times 2 is 4 times 2 is 16 equals 4 times 2 is 8 plus c. So let's subtract 8 from both sides. We get c is equal to totally not 16, but totally is equal to 8. So a couple other bonus things I want to talk about here. How do you check your work on a calculator if you have access to one? So pretend like, no, let's ignore that graph I just put down. Let's go back to, say, this problem. Let's do this one that we didn't actually do. So let's say you went through and you did all this by hand and you got these answers and you want to check yourself. What should you do? Well, you should write the equations. You should graph y1. I don't want to do that in green. You should graph y1 equals kx squared with your k value plugged in. So negative 3x squared plus 9x plus our c value, so not plus, but minus 75. You should graph that as y1. You should graph y2 as your other function, 7kx. K is negative 3, so we get negative 21x. You should graph these two functions. You should find a good window. You should trace to the x value of 5 on y1, get the corresponding y value. You should trace to the x value of 5 on y2 and get the corresponding y value and make sure that they are the same. You should then do another feature. So if you have these quadratics, the quadratic and the linear function, so they're looking something like that, I don't know. But we have these two things. What you should do is go to second calculate. So as always, second calculate. Option number 6 says dy over dx, which represents the derivative of y. So choose option 6 for dy dx and press the up or down arrow to jump between graphs, and then type in the x value that we want. We want the x value of 5. It'll tell you the derivative at that point without having to sketch the derivative function. And voila, you know the derivatives. Check on both graphs and make sure they are equivalent. You have just verified that your answer is correct. So I want to take you on a quick mental journey. So think about this function, y equals x cubed. Y equals x cubed is an interesting function because think about the derivative of this function, y prime equals 3x squared. If you think about the derivative of this function, we know this derivative has a 0 when x equals 0. That tells me that if I were to draw the tangent line here, it would be a horizontal line on the x-axis like that, because the value of the derivative at that one specific point is 0. So that tells me that this graph, for a very, 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 very ever so brief, fleeting, instantaneous moment, has a derivative of 0. So compare that then to the inverse of that blue function, y inverse, which is the cube root of x. If that blue function is x cubed, then I can draw the inverse function by swapping all my x and y points. So remember the key idea of inverses. You can swap the x and y values. So if the blue function is x cubed, this red function is the cube root of x. And think about that tangent line at the x value of 0 then. This function was flipped. Remember when you're sketching the derivative, the inverse of a function, it flips over the line y equals x. So that tells me that that tangent line there, instead of being a horizontal line on the other function, is a vertical line right there. So we can't actually even write the equation of it other than saying x equals 0. But this has pretty interesting implications for the derivative of the cube root of x. So think about the slopes of all these tangent lines. If you think about, say, like that tangent line, I'm a really low number, like almost 0. And then I start to get a little bit bigger, a little bit bigger, a little bit steeper. And then, like up in this zone right here, it starts to go crazy, and I start to get steeper and steeper and steeper as I approach that vertical line. And then on the other side, I'm getting less steep abruptly, less steep abruptly, less steep abruptly, less steep, and then I'm shallowing out back to 0. But the whole time, my derivative is positive, but it's 0, or very close to 0 out there, and then all of a sudden it shoots off towards infinity. Choo! And then on the other side, it comes back down, and then it mirrors it like that. Holy moly, what just happened? Well, think about what happens when you take the derivative using the power rule. Our red function is x to the 1/3. So when I take the derivative of x to the 1/3, power rule says I'm going to get 1 over 3 times x to the 2/3. So if you think about the x value of 0, 0 squared and cube rooted is 0 times 3 is 0. So I get 1 over 0. My derivative is undefined at x equals 0. That's why I'm getting that vertical asymptote right there. Whoa. So this function has a derivative that is not continuous. Since the derivative is not continuous, this function is not differentiable. So even though we were able to come up with a more or less normal function, the derivative of this function is not continuous. We get that weird vertical tangent line there, and so this function is not differentiable. So just because it's not a piecewise function doesn't mean it's automatically differentiable. Think about another situation here. Think about the function, say, y equals the absolute value of x. Well, that function is going to look like that, ba-boom, and ba-boom, like that. The slope on the right is +1, and the slope on the left is -1. So if you were to graph the derivative of this function, you're going to end up with the absolute value of x over x graph. Whoa, that's crazy. So much stuff is falling together. But since that derivative is not continuous, we know that this function is not differentiable. Also, notice the sharp turn there. We have an instantaneous change of slope from a negative value to a positive value, showing us that it's not differentiable. So if it's pokey like that, it's not differentiable. Can you think about another function that is pokey like that? Say, for example, y equals x to the 2/3. Well, y equals x to the 2/3 is our bird graph that looks like that. So now again, think of the tangent lines here. As I am coming in from the left, I'm negative, kind of not super steep. Then I'm getting steeper and steeper and steeper and steeper and steeper and shooting off towards negative infinity. And then all of a sudden, immediately, I'm then positive, like positive infinity, positive, 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 positive. Holy cannoli, but again, like less steep on the outer bits, so like negative, less steep there compared to like super negative and super positive right there. But again, I'm going from essentially a negative infinite slope to a positive infinite slope absolutely immediately. So if you were to sketch this tangent function here, it's going to end up looking something like that. Now, I know it looks like a 1 over x graph, but we know it's not, because if you were to take the derivative of this function, again using the power rule, we're going to get 2/3 over 2/3. Oh, blah, 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 how do I want to say this? 2 over 3x to the 1/3. So we're actually getting x over 1/3, but again, since we get the 0, x value of 0 makes that function undefined, we get that asymptote there, so we know the derivative cannot be continuous there, hence not differentiable.